Hi guys, today we're going to be learning about alkenes. So first I would like to give you a general overview on this topic. The first thing that we're going to be discussing is general properties, and we're going to be looking specifically at bond angles. So in this case, the central atom, the one that I've highlighted in blue, has three regions of electron density around it. So we have a hydrogen, another hydrogen, and a carbon. So in this case, it's going to be 120 degrees and it's going to be sp2 hybridized. So this is going to be ethene, and this has been covered in detail in the chapter of bonding. So now let's discuss hybridization. In this case, when you're forming this carbon-carbon double bond, two p orbitals are going to overlap with each other and they're going to form a pi bond. In this case, the pi bond is very rigid, which leads to hindered rotation, and it's also a high region of electron density, which we're going to be discussing more during reactions. After this, we're going to move on to the preparation of alcohols, and then we're going to be discussing the reactions. So the reactions in this case are going to be combustion, you have electrophilic addition, oxidation, and polymerization. Now let's move on to preparation of alkenes. So there are two methods to do this, and the first one is called cracking, which has been discussed in detail in the alkanes videos, which you guys can go check out if you're interested. But I'm going to give you a basic overview of what it is. So in this case, we're going to be talking about two types of cracking, which one of them is thermal. So cracking is basically splitting up of larger molecules into smaller, more useful molecules. So the first type of cracking is thermal cracking, in which you're going to pass steam at 800 degrees Celsius over the large molecule, and then it's going to split into smaller molecules. The second type is catalytic cracking. So in this case, you're going to use a catalyst, which is Al2O3, and this is going to be split into alkenes. So this is the first way to form alkenes. The second way is dehydration of alcohols, which has been covered in detail in the alcohols chapter. So this is the apparatus that you use for this. In this case, you're going to have mineral wool, which is soaked in ethanol. And you're also going to have your catalyst, which is going to be Al2O3. And alternatively, you can also use H2SO4 as the dehydrating agent. In this case, you're going to heat this mixture, and you're going to use downward displacement over here to collect this gas over water. So this is going to be ethene, and this is going to be a Bunsen valve, which is basically going to stop the water from going back into the tube. So in this case, the gas is going to be collected over water because it's insoluble, and we're using it downward displacement because it's lighter, it's heavier than air. Alkanes. Now we're going to move on to the reaction. So the first reaction we're going to be discussing is combustion. So complete combustion is going to lead to the formation of carbon dioxide and water, and incomplete combustion is going to form carbon monoxide and water. So alkenes are going to burn with a sooty flame. This is because the carbon to hydrogen ratio in alkenes is going to be greater compared to the carbon to hydrogen ratio in alkanes. And as the number of carbon-carbon double bonds increases, the smoky character of the flames increases. Combustion has been covered in detail in the alkanes chapter, and the general gist of it is the same. So if you want to learn more about it, you can watch the videos for that. Now we're going to move on to electrophilic addition of halogens. In this case, you're going to have ethene, and you can use any alkene for this. For this example, we're going to be using ethene. So in this case, as we've discussed before, the pi bond is a region of high electron density. Because of that, it's going to induce a positive dipole in the neighboring chlorine. And since a positive dipole is induced over here, you're going to get a negative dipole on the other chlorine in this case. And now you're going to get a dative bond between the carbon and the chlorine in this case. And it's very important to make this arrow from the double bond and not from one of these carbons and towards the chlorine. Because of that, this bond is going to break heterolytically, and in this case also you need to make the arrow from the bond and not from the chlorine. And this is the mechanism that you're going to show when they ask you in your examinations to make the mechanism. So in this case, this carbon is going to be positively charged because this chlorine is attached over here and the double bond is broken, so this carbon has 3 bonds instead of 4. So this chlorine over here, which is now negatively charged as it has 2 extra electrons, so in this case what's going to happen is that this lone pair, you're going to make a dative bond from the lone pair towards the carbon over here, and then in this case you're going to get an alkyl halide. Now let's look at the general equation for this reaction. So in this case you're going to have ethene. It's going to react with chlorine. In this case, the condition for this is that it needs to be dissolved in some sort of... The condition for this is that it needs to be dissolved in a solvent. So in this case, normally we use hexene as it's non-polar and it won't react with the mixture. The next thing that we're going to be talking about is the electrophilic addition of bromine. So in this case, the reagents that we're going to be using is going to be aqueous bromine. So previously we used bromine dissolved in our organic solvent, which was hexene. And now we're going to be talking about bromine dissolved in water, which is going to be aqueous bromine. So in this case, the conditions are going to be that it's going to be at room temperature, and this is the general equation for the reaction. So you have an alkene reacting with aqueous bromine, and it's going to form a bromo alcohol and hydrogen bromide. So this is going to be electrophilic addition of bromine. So the first thing that happens in this case is like we discussed before, this pi bond is a region of high electron density. So this is going to induce a positive dipole over here, and a negative dipole is going to be induced in the other bromine. So in this case, this bond is going to break heterolytically, and you're going to get bromide ions. After that, this bromine is going to get attached to one of the carbons, and the double bond is going to break, forming a single bond. So because of that, there's going to be a positive charge over here because as you can see, the carbon has 3 bonds and not 4 bonds. So since this is positively charged, it's going to attract a negatively charged ion. So in this case, you have a bromide ion, and you also have a water molecule which has a lone pair, which can be attracted to the positive charge. So in this case, since this water is going to be in excess, it's going to be attracted to the carbocation more. So in this case, the water molecule is going to get attached to this positively charged carbon. And after that, since this is very unstable, because this oxygen has 3 bonds and it's positively charged, the bromine is going to get attracted, the bromide ion is going to get attracted to this positive charge, and you're going to get a bromo alcohol and hydrogen bromide. Now we're going to be discussing the electrophilic addition of hydrogen halides. So for this, the reagents will be a hydrogen halide and an alkene, and the conditions will be that it's at room temperature and the gas will be bubbled through the alkene, the gas being the hydrogen halide. So this is the general equation. The alkene is reacting with HBr in this case, but you can use any other alkyl halide to give you you can use any other hydrogen halide to give you an alkyl halide. So in this case, as discussed previously, the pi bond is a region of high electron density. There's going to be a dative bond formed between the pi bond and the hydrogen over here. So you're going to make an arrow from the bond to hydrogen, and this is going to be partially positive because HBr is a polar molecule since bromine is more electronegative than hydrogen. And then you're going to make the second dative bond. Basically, this is going to break heterolytically. So you're going to make an arrow from the bond to this bromine, and then you're going to get a bromide ion. So after this, similar to the reactions that we've done before, this is going to be positively charged, so you're going to have a carbocation, and this is going to be attracted by this bromide ion that was already produced over here, since this is negatively charged and this is positively charged. And you're going to get an alkyl halide. So the next reaction that we have is electrophilic addition of hydrogen gas. So this is used to convert alkenes to alkanes, as you can see in this equation. You have ethene that's turning into ethane by the addition of hydrogen. So in this case, the conditions are that you use a nickel catalyst at 140 degrees, or you can also use a platinum catalyst at room temperature. And the commercial use for this is that you use this to convert vegetable oil to margarine. Now we're going to be talking about the electrophilic addition of steam, which is our last electrophilic addition reaction. So for this, our reagents are going to be an alkene and steam, and the conditions are going to be that it's going to take place at 300 degrees Celsius at 70 atm. And phosphoric acid is going to be the catalyst, and it's going to be adsorbed on silica. So in this case, the first thing that's going to happen is that this acid is going to dissociate into an H+ ion and a phosphide ion. So in this case, after this, what's going to happen is that, as I said before, the pi bond is a region of high electron density. So in this case, a dative bond is going to be formed between these electrons and the hydrogen, and then you're going to get this intermediate, and a carbocation is going to be formed. So in this case, the carbocation is going to be attracted to this water molecule since the addition of steam. So in this case, this is going to form a dative bond. So a dative bond is going to form between this carbon and the lone pairs of this water molecule. So after this, you're going to get this intermediate again, which is going to be pretty unstable because in this case, oxygen has 3 bonds and it has a positive charge. So after this bond is going to break heterolytically because of the conditions that you have over here. And then you're going to get an alcohol, and the catalyst that you were using will be regenerated. Previously, we only discussed alkenes that were symmetric, like this alkene. But now we're also going to be talking about unsymmetric alkenes. As you can see over here, there's this methyl group, and over here there's no methyl group. So this alkene is going to be classified as an unsymmetric alkene. First, let's talk about the different types of alkenes. So the first one that we have is primary alkene. In this case, the carbon is going to be bonded to 2 hydrogens over here. In the secondary alkene, the carbon is going to be bonded to 1 R group and 1 hydrogen. And in a tertiary alkene, it's going to be bonded to 2 R groups. So in this case, the stability is going to increase, and we're going to discuss why. As you go down this arrow, stability increases. So in this case, for a primary alkene over here, this is a primary alkene that I've drawn over here. This is going to be the least stable in this case. For a secondary alkene, this is what a carbocation is going to look like if you have a secondary alkene. So in this case, the electron density of the alkyl groups over here is going to feed towards this positive charge, and this is going to lower the overall value of this positive charge. So this is known as positive inductive effect. So as you go down this arrow, the positive inductive effect is going to increase in this case. So now in this case over here, since you have 2 different R groups being attached to this carbocation, it's going to lower the intensity of this positive charge even more. So the lower your positive charge, the more stable the product. So which is why as you go down this chain, the stability increases. And on the next slide, we're going to talk about how this influences what type of carbocation is going to be formed.